Hi, in this video I'm going to show how to use Halide cogeneration to accelerate the performance of image processing algorithms, in this case optical flow, for C++ cogeneration from Simulink. Halide is a language developed by MIT in 2012 to accelerate image processing algorithms, and Simulink cogeneration is leveraging it, and the autoscheduler developed by Andrew Adams in 2019 that uses deep learning for finding the optimal schedules or optimizations for these image processing pipelines. At the end, I'm going to briefly mention how this can be applied for deep learning convolutional neural networks as well. Okay, before entering into the details of the example, which is very easy to use Halide, it's just basically a flip of a switch, enabling a config set parameter, that's it. But I'm going to give you some background about Halide. As I mentioned, this language, it can be seen as a language, but it's really like a library that looks like a language within C++. It basically is functional, behaves functional, there, it doesn't have cycles, and basically is designed basically to target the image processing algorithms which usually involve stencil operations. For example, when you talk about convolution, max pooling, average pooling in convolutional neural networks, those are stencil operations. Okay, let's give some background before entering into Halide. Let's give some background in what are stencil operations. For example, the convolution is a stencil operation. What that is? You have an input image and an output image in the operation. And the output pixel, one output pixel depends on the corresponding input pixel and the neighbors. So in the case of convolution, you multiply this kernel, this window kernel, by a weight kernel. And then that is reduced into a single pixel, and that becomes your output. In the case of average pooling, you take the average of all the elements, and that's your output in one element. In the case of max pooling, you take the max, and that's the output. That is a stencil operation. A point-wise operation or an element-wise operation, the output depends solely on the corresponding inputs, and that's it. So that is equivalent to having a kernel window of 1 by 1. In this case, the window is 3 by 3, but if it's element-wise, it's 1 by 1. Okay, what happens? For example, in deep learning, if you have a convolution and a ReLU, one is a stencil operation, ReLU is a point-wise operation. In that case, the fusion is trivial, and most of the frameworks do the fusion between convolution and ReLU. That's easy. But what about when you have a convolution, ReLU, and max pooling? You have a trio where two of them are stencil operations. So if you do full fusion, it's not going to be that optimal because you're going to have you're going to do bad in the trade-off between redundancy, parallelization, and locality that Halide is designed to optimize. So the autoscheduler of Halide is going to find the sweet spot in that triple trade-off using partial fusion. For example, you can do fusion between convolution and max pooling, but it's going to be at some level of a for loop. Because when you do operations in tensors, in multidimensional arrays, those becomes nested for loops in C++ when you lower them. And you can do fusion using, for example, the computer Halide. Let me go to the tutorial. This is a tutorial. I'm gonna put all the pages that I'm showing. I'm gonna put them as references in the description of this video. So in here you can see Halide that one of the key features of Halide is a separation between computation and schedule. You have the computation, which is a pipeline of a producer. You have a trigonometrical operation, and then you have which is a pointwise. And then you have a stencil operation because it depends. You can see the plus one, and it creates a neighborhood, a kernel by using the plus one. You have two pixels in here, the XX and the X plus one, Y plus one. You have a window in here, so it's a stencil operation. So with that, at the end, it's gonna do some experiments. I'm gonna show that, and it's gonna go from a trivial schedule, which is basically something as simple as this. It's gonna go to an optimized schedule, which is something like this. And you can see this computer, which is a partial fusion. This is something, why I'm emphasizing in the partial fusion, because it is not trivial to manually do this in a manual optimized library. This is something that a compiler can take advantage, and that's what Simulink does. Simulink in code generation is taking advantage of, with the autoscaler, of doing partial fusion, something that the manual optimizers can do. So in addition to do the usual optimizations like parallelization, SIMD, tiling, which is good for cache, and all of that, and also it has a memory, the granularity of the memory can be controlled partially with this store at a schedule primitive. So there's a lot of details, but the main takeaway is that Simulink is going to take advantage of compile time information to optimize this. You don't have to worry about any of those details because, again, you just enable Halide cogeneration by a flip of a switch that I'm going to give you in detail now. Okay, so the optical flow algorithm that I'm going to use in this video is the Lucas-Kanade. You're going to find it in details about this algorithm in this article. It's going to have a combination of stencil operations and pointwise operations. I'm going to show you the model. Let's go to here. Let's just first clear the folder to begin over again. Okay, so for this example, you can use the command at the top to open the example. I just copied the files to another location. Okay, so here's the optical flow model. The optical flow model is going to use the neighborhood processor subsystem block, which is basically a relatively new subsystem in Simulink, which you can specify a stencil operation. So you can see neighborhood, the word neighborhood, because it's a kernel. In the kernel, you specify the size of the kernel. So you have a 1x5 kernel window in here. If you specify 1x1, then it's going to be a element-wise operation. The good thing about this is that you can do an element-wise operation, a stencil operation, and say, without specifying the for loops. When you don't specify the for loops to a compiler, the compiler can do the operations in any order, which means that you can parallelize it and do whatever optimization. It's more powerful for the compiler. So in here, we have a reduction. So you have a kernel window of 1x5 that is multiplied by a constant, this constant over here, and then it's reduced by the sum reduction. So you're going to have 1 pixel. In the neighborhood processor subsystem block, the output is going to be a scalar always, but you will have usually a multidimensional array, small one, a small multidimensional array in here. But that small multidimensional array comes from a larger array that comes from here, which is the image. And this is followed by a pointwise operation and then more stencil operations that are reductions in here, and etc. So this is the algorithm right here. Okay, so now let's try first without Halide. But first, to measure the performance, let's do some settings. We're going to go to a seal pill. To find the seal pill, if you don't have it, you just can search in apps in here. You can search for seal pill manager, and it's going to appear in here. And then you do the settings, and in the settings, you make sure that you measure execution time. You set it to coarse because we at this point we don't need the details, and you set the workspace variable and all the data. Disable debugging, make sure this debugging is disabled, the coverage is disabled, and in data import export you enable this single simulation output. For the code generation, I'm gonna disable Halide code generation. This is the only thing that you need to set for Halide code generation. I'm gonna disable it because I want to see the performance first, and then I'm gonna just run verification. It's gonna compare the numerical values between normal simulation and seal, and we're going to get the performance number for seal. We're going to see in a moment. One thing, first the Rhino is going to execute. You're going to see the animation of the Rhino in here. You can see the optical flow in normal simulation where the Rhino is marked because it has some movement. And now it's going to do code generation for seal, and it's going to measure the performance. One thing to notice is that the antivirus might bother thinking that it's not safe. So you have to sometimes you might have to disable your somehow your antivirus so that it doesn't complain, or you can let your antivirus know that it is safe. For example, in this case, it's complaining, and it might realize. Sometimes it realizes that it's safe, but sometimes you have to manually create an exception for it. Okay, I'm gonna pause while it finishes. Okay, there are 6 of them, so that might be the last one. Actually, it's the last one because this is executable. So I'm gonna quickly show you the generated highlight code. Okay, so let's open it one. You can see that there's not much fusion. We have the sum reduction that I just showed you and the multiplication of the constant, the gain constant. And you can see that this is a stencil operation because it's going outside the center of a window, and this is the center of the window plus some reduction variables. So this is Halide has the separation, as I mentioned, the separation of computation and schedule. So this is the generate has the computation, which is very simple, formula for the operation, and then you have the schedule. And for the schedule part, you can manually specify the schedule here, uh, but instead, we just use an autoscheduler and we just have to specify, and this all is generated automatically. And the automatic code generation is going to specify the limits of each dimension. Then the deep learning based autoscheduler is going to find the optimal schedule for this particular algorithm. And that's going to happen for each pipeline that you find in here. Let's pick up another one, like for example, the ones that end with Halide CPP are the pipelines. Yeah, so let's see how fast it was able to execute. Let's go back to the model. You can see that it took 3 seconds. So it's almost 10x speed up. And the maximum was hmm, yeah, 2.8. That is weird. That is weird. Why the average is larger than the maximum? But anyway, the average is about 10 times is faster than. Okay, so let's do something to improve the coverage of Halide because, as I mentioned, these blocks are not going to make it into Halide, but we know that they are pointwise operations, so we can copy this, put it here, and we're going to wrap this in a pointwise kernel. So we're going to copy this block, going to put it inside of here, delete this, just connect it. This has 2 inputs, so we have to create an additional input and just connect them. Okay, and now we're gonna make this a pointwise operation. A pointwise operation is a kernel of size 1 by 1, so we just put 1 by 1 in here. That's it. So now we have a pointwise operation, and then we just replace the existing one with this. Make it small and make it fit. Whoops. Okay, now we effectively wrap this pointwise operation in a neighborhood processor subsystem, and what it's gonna do is gonna fuse this into a single Halide pipeline, which allows the partial fusion that I discussed earlier. So you can do this for the rest of them, for this one, this one, this one, and this one is a pointwise operation. And if you go down here, this is already wrapped in the neighborhood processor subsystem block. But this one also can be wrapped as well, the whole thing. But there's a caveat. Halide code generation doesn't tolerate and Boolean outputs. So we're gonna see how I did it. I'm not gonna take you through all of that. I just have the model already made in here. So I'm gonna open it and let's take a look. So I wrapped all this in neighborhood processor subsystem blocks and all of this. Now we can have fusion for this. And then I also wrap this into a neighborhood processor subsystem. And as I mentioned, Booleans are not allowed, so I cast it to uint8 so that I can get these Boolean operators inside the neighborhood subsystem block. And then in output, I cast it back to Boolean. So that's a trick to be able to get everything into Halide. Okay, so now let's notice that before we had like 6 pipelines of Halide or more. Now with that, let's see how many pipelines we get. The less we get and the more code we get, the better. So let's run it and let's go to seal and just run it. The configuration is the same. And you're gonna see that we have Halide code generation enabled, code generation, Halide is enabled. So let's just run it. And again, you're gonna get the warnings. I'm just gonna pause it. There you can see the running Rhino here. Okay, now it's gonna do code generation. That's for normal simulation. Zero simulation behaves the same. I'm gonna pause while it finishes generating code. Okay, still we have only 3 pipelines now, and you can see that there's more fusion now. We have these pointwise operations, but also, well, this appears stencil pointwise, pure pointwise operation. So this is trivial. Most likely, this is not going to require partial fusion or just regular parallelization and SIMD. Okay, for this one, there's a stencil operation here and another stencil operation. So you have a probability of using computed a partial fusion between these two. So that gives more power to the deep learning based autoscaler of Halide. And then you have more. So we have bigger pipelines, and that's good. The bigger the pipeline and the less pipelines, the better, because Halide can get more power. Okay, so we're gonna see in a moment how that looks in the final product. Okay, it finished compiling, and now remember that we had 3 seconds, so we brought down the performance from 3 seconds to 2.4 seconds. So it's faster now. We have more fusion, more optimizations for Halide. Okay, so what you're learning here for a classical image processing algorithm can be applied also for convolutional neural networks, because Halide can be used in Simulink for the convolutional neural network block and also for other blocks. So how to do that? I'm gonna show you in a moment. So there's a page, this article I'm gonna put also in the reference, when to use Halide. If you have a deep learning based model, let's say a ResNet 18 or something like that, you can use the export network to Simulink, and it's easy. For example, you can try it yourself. You can use this command, image pre-trained network, where you create a pre-trained network. It can be ResNet 18, ResNet 50, and you just use export network to Simulink. So you're gonna convert the deep learning neural network into a Simulink model with this command. Once you enable it with that, again, you can use the command this one, set param bd root Halide code generation to enable Halide, and then you just generate Halide code. That's about it. It's a couple of commands to try deep learning convolutional neural networks with Halide. So if you see that the performance is better than the Simulink Predict block using the same deep learning toolbox neural network, then you can switch to Halide if you find it that performs better. Okay. Okay, so that's it for the video. If you have any questions, please let me know. Thank you very much.